So, all of this theory leads us to the exciting world of quantum mechanics. Some of the names you should know are Schrödinger and, of course, Einstein. These were the leading men of quantum mechanics. However, they actually didn't really think that it would work, so they came up with all these theories. And especially Einstein at the end was showing these theories in the sense where he was saying, quantum mechanics can't be real because then this and this and this has to happen. And later they found through experiment he was right, that those things did exist, which was really awesome. And there's a great book on Einstein's life that actually goes into details and letters from between him and Schrödinger about quantum mechanics and theories, and that's actually where the Schrödinger's cat example comes from. Anyway, so that's a little history lesson that will not be on a test. So Schrödinger proposed an equation, and we have seen that electrons can act both as a wave based on de Broglie's equations, and they can act like a particle. Now, quantum mechanics combine these into the wave-particle duality theory, which states that a wave function of electron depends on a kinetic energy and potential energy of an electron. Now, this equation you do not have to memorize at all. I just showed it to you so that way you can see that what we're covering is actually way more complex than what we're going to go into. So if you don't understand something about quantum mechanics, that is okay. The material that we're going to cover now is just giving you an introduction to the complex world of quantum mechanics. But what you do need to know is that this equation leads to what we call a wave function. Okay, so this equation is used to describe an electron and light as both a wave and particle. And this wave function is what we're going to call orbitals. And this is where we're going to find an electron. Now remember, we can't know the position of an electron very well, so we have to go into solving the probability of finding an electron somewhere. And so the wave function squared gives the probability of finding an electron in some region of space. And this region of space is called an orbital. And these orbitals have shapes and spatial orientations. So they're not just a 2D representation that we've been seeing. They're actually 3D. And they describe the spatial distribution of electron density. And this is just another way of saying, where's the electron? Okay. But this orbital wave function is described by four quantum numbers. So we already know one of them, which is the principal number, n. And when we solve the wave function, we get these four sets and their energy, and we get the electron density. So visibly what this means is if you plot the probability of finding an electron in an orbital these blue dots represents high density, so where you're more likely to find an electron. As you can see, you have a low probability of finding it as you go out. So we don't use this. We try to make it simple. So this would actually be represented by a sphere instead of all these dots. So again, we talked about the quantum number n, and this n is the same we talked about with Bohr's and de Broglie, or the other energy equations. And we already know that it has to be an integer number. Now, this says that n can be this, but it actually can be any number. Okay, any number greater than 1, greater than or equal to 1, n cannot be 0. Now your book says n is equal to 0. This again is one of those examples where your book has a few errors. And you might hear that we call the n is referred to the shell. Okay, so these shells of the orbitals is represented by n. We also have the quantum number L. And this L is dependent on the values of n, where L can be 0, 1, and so forth, up to n minus 1. So if you have n equals 2, then it can be 0 or 1. L is not negative. And each of these numbers have a corresponding subshell. So you are required to know this and have this memorized for the first 4 L numbers, subshells, where 0 is called the s orbital, 1 is equal to the p orbital, 2, d, and 3, f. So please have those memorized. Now, we can have other types of orbitals, and they do go on, but those are the only ones that you have to memorize, okay? The third quantum number is called the magnetic quantum number, and that's m sub L. And this depends on L. And so what this gives is a 3D orientation of each orbital. And it has the values of negative L, 0 to L. So if you have an L of 2, you can go negative 2, negative 1, 0, 1 to 2. Okay. But what does this mean? We'll go into depth in a moment. So those are the 3 quantum numbers that we can actually we can get from the Schrödinger equation. There's a 4th that's called the spin, and that's m sub s. And this is not directly related to the Schrödinger equation, but it does give us more information about how to locate the behavior of the electron. So in the 1920s, it discovered that 2 electrons in the same orbital do not have the same energy. They have opposite. So we call that the spin of electron, and describes the magnetic field. And remember that the magnetic field and the energy can be related. So this leads to a 4th number, and we call that the spin quantum number. There's only 2 values of m sub s, and that's a positive 1/2 and a negative 1/2. So a great way of visualizing this is the principle principal quantum number gives you the general location of the electron. So let's say if you relate it to an address, it tells you the state you're in. Okay? And there's a certain amount of states that you can be in. The L gives you a more specific location of the electron. So instead of just saying the state, it knows what street you're on. And there's only a certain amount of streets available. Now, the M sub L tells you which house you live in on the street. So in this case, this would say that you have you have an L of, let's say you're on street 1. So you can live in house -1, 0, or +1. The M sub S tells us who to address the letter to. So if you and your roommate lives there, so I just chose Einstein and Marilyn Monroe because there was pictures of it, then one of them would be a +1/2 and the other is a -1/2. So there's only 2 people that could live in this house. What you have to know are these 2 boxes. You have to know the subshell, the number of orbitals in the subshell, and the maximum electrons in that subshell. Now, when we write the subshell, we can look at the periodic table too. So we have a nice cheat sheet. So you can memorize these boxes, or you can start by looking at the periodic table. So remember that the periodic table was designed so you have increasing atomic number, but the general shape of the periodic table also tells you about the quantum numbers also. So we know that the principal quantum number will be the period number. So we have 1. So n is equal to 1, 2, 3, 4, 5, 6, 7. Okay, and that's true for the main group elements. And they correspond here. Where the left side is the s orbital. And you see there's only 2 boxes. So you know in the s orbital, you could only have 2 electrons. So 1s would have 1 electron here, 2 electrons. In the p orbital, it holds 6 electrons. 1, 2, 3, 4, 5, 6. In the d orbital, you can count it, and there's 10. And in the f orbital, there's 14. So you can look at the location of the element and learn more about the energies of the orbitals. And we can write that as the electron configuration, where hydrogen would have the electron configuration of just 1s1. So you're in the period 1. You have the L of 0, so that corresponds to S, and there's 1 electron, which would be written as a superscript. So it would be 1s1,